I think it's probably safe to say that open source won the battle of how software is developed.
Und was wir jetzt tun müssen eigentlich als IT ist, wir müssen es schaffen, nicht unsere eigenen Prozesse zu optimieren, sondern wir müssen die wahrgenommene Geschwindigkeit optimieren.
Constrained by processes that were made for a different era, were made for a different world, a world of certainty.
Be comfortable with the fact that you don't know, no one's going to know everything, and if this is still something that's scary or something that's new, that's okay, and that's normal.
So a mechanic can look at the car and analyse what's wrong with the car. You can look at your code and go, I'm expecting this outcome, and so I can close that gap.
Doch, es geht. Ja. Das heißt, wer jetzt richtig Bock hat, das nochmal mit dieser Technik anzugucken, kann rübergehen. Bitte nicht alle gleich noch brauchen, sind wir ganz allein. Das ist schade. Auch schade für unsere Keynote-Speaker. Aber wenn man richtig Bock hat, kann sich das mal angucken. Sieht schon ganz gut aus. Ich habe es zwischendurch auch mal angeschaut. Okay, jetzt zur angekündigten Keynote heute Morgen und heute Mittag schon mal kurz erwähnt. Aus Sicht der Java-Softwareentwicklung ein kleines bisschen off-topic, aber trotzdem relevant. Die Idee, heute Morgen schon mal kurz besprochen, Under the Hood, Hashtag Under the Hood, sich ein bisschen mit Themen zu beschäftigen, die nicht wirklich notwendig sind, aber sozusagen die so ein kleines bisschen diese Faszination an Technologie vielleicht auch zurückholen und auf der anderen Seite natürlich auch mit dem zu tun haben, womit wir alle eigentlich tagtäglich fast zu tun haben. Und hier geht es um HTTP, die nächste Version HTTP 3. Und I'm switching to English. Daniel Steinberg is giving us an introduction, what's going on with HTTP3. He's working on that specification, and he's also, for some people of you, quite well known as the developer of the networking tool curl. And well, I'm really curious to learn something about networking in the age of HTTP3. Please welcome Daniel.
Okay. I'm just going to reset my camera here to make sure that I stick with my time. Okay, HTTP3 in 30 minutes, go. I'm Daniel Steinberg, as also was mentioned. I did curl. I actually started 24 years ago, so I've been doing HTTP programming a while by now. nowadays, I'm employed by Wolf SSL. I do curl full-time. So a lot of my work within HTTP started about 10 years ago when I got involved in the work that IETF is doing, basically working on specifications for HTTP and a lot of other protocols, but my prime interest then and now it has been within HTTP and related protocols. And IETF is the organization, Internet Engineering Task Force, that is nowadays working with the HTTP 3 specification and QUIC. So, who is involved in this then? IETF is an organization where everyone can participate, but some of the companies that have people involved in the IETF and QUIC and HTTP 3 are these rather well-known web content companies. So a lot of interest from a lot of well-known companies in this fun protocol, HTTP 3. So, but looking back, HTTP it started back in the old days. It's actually part of the Tim Berners-Lee vision for the web back in late 80s, and HTTP 1 came in 1996 originally. It was specified then, and it took 16 years, and then HTTP 2 came, and now we're talking about HTTP 3 already. So that's basically the foundation for all this. And you know, HTTP, it looks like this. Beam, get stuff, your headers, and you get the headers back in response, and yeah, that's HTTP. Let's not care about that right now. So HTTP started, or we're still using it, over TCP, that protocol. TCP is I try to envision it like a chain with individual links, right? It comes in that order, and it makes sure that the link is intact all the time. So it's done over IP, and it establishes a connection, and we do a handshake to get that. There's a three-way handshake, you know, ping, pong, ping, syn, ack, and we have a connection then. And it makes sure that if you lose a packet somewhere, it waits a while and it sends it again. So it keeps an established connection, and you know that the packet you send in one end, it will arrive in the other end, or fail completely, but it'll end up in that order, so it delivers a byte stream between two hosts on the network, and it's in clear text. So anyone on the network can read what you're doing over TCP, right? So that's TCP, standard basic. And we've known it for years. It came in the 1980s, right? Basically it's been improved, but the basics have been there for many decades. So then we introduce HTTPS, right? Which is that TCP and HTTP, but we also add TLS. And if we look at the data right now, this is data from the Firefox telemetry. We can see that basically somewhere around 80% of all the web page loads today that the browsers are doing are done over HTTPS. So we can see that HTTPS is really the new norm, right? HTTP was in the past. Nowadays we do everything HTTPS, or more and more HTTPS, and the trend is clearly, well, it's not straight up, but I think it's going to go up even further. So somewhere around 80%, maybe in a year or two, we're going to 90%. So a lot of HTTPS. And HTTPS then is done with TLS. TLS, of course, is done for this. So that's the extra layer of security we had. So we had another handshake on top of the previous TCP handshakes to get an extra secure connection over TCP, so that we get privacy and security over between two endpoints over the network. Not that complicated. Well, it's fairly complicated, but the concept is easy. So we've done HTTP over TCP as a concept for a long time. So we started then, as I mentioned, let's go back to just sort of the basics how it works. HTTP 1.1. The first 1.1 spec was made in 1997, quite a long time ago. So it has a lot of problems with HTTP. It's very back and forth, ping pong. We have to wait, we send a request, we wait for the response. It takes long, so we wait for the response and the server waits for the next request. A lot of waiting. So to compensate for all that waiting, we open more connections so that we can do ping pong over many connections at the same time. A standard browser today uses 6 connections for each host name. And if you're running a site today and you think 6 connections is a little bit bad, you want more, you just invent new host names for your host and you get more connections. So we get a lot of connections, all of those doing ping pong, to the extent that a browser these days usually just fire up a connection, it makes one request and it closes the connection again because it has too many connections. We can't have that many connections, close them down. And that's really ineffective because as you know, maybe you don't, but now you know, that TCP is really slow in the beginning. It has a slow start period. We need data to get up to speed. And if we close it immediately after the first request and response, we probably never even got up to full speed. So we just open a lot of TCP connections, they never get up to full speed, and we close them again. And we open new ones again. Not a good idea. So back in the HTTP 1.1 days, we did also then introduce or suffer from the HTTP head-of-line blocking, which means that we have a limited number of TCP connections, 6 per hosting, and we want to download 200 images from a website over 6 connections. Which connection am I going to send my next HTTP request over? It's complicated. There's always another one ahead of you. Which connection are you going to use for your next HTTP request? Complicated. The head of line is blocking you for your next request. A really complicated issue for browsers. Complicated. So over time, sites users have introduced a lot of fun workarounds for that, but I'm going to skip over them because we solved a lot of those workarounds when we introduced HTTP 2. It was shipped in 2015. I'm going to stand further towards you. So it shipped in 2015, 16 years after the big 1.1 spec. Took a long time. There was actually a 1.1 update the year before, but let's skip, we cannot care about that. With HTTP 2, there was a strong emphasis to reduce the number of connections for each host to just down to 1, because now suddenly we could take advantage of TCP properly. We can let it get up to speed, and we could use TCP, saturate the bandwidth, both directions, thanks to us doing many streams over the single connection. So one TCP connection, and we did logical streams over that connection. Nice, we could suddenly have 100 or 1,000 streams over one single connection. That was really awesome, until we figured out that, oh, right, now we have one TCP connection, but what happens if you have packet loss? You lose one of those packets, all of those 100 streams, they have to wait for that single packet that was lost to get transmitted again, and suddenly 100 streams can continue until the next packet is lost. Then 100 streams have to wait, and yeah, not ideal, but it was still a big step forward. And then, of course, we have, over time, on the internet, this isn't really just HTTP, but we have introduced an internet where we suffer from this thing we call ossification, because this is how the world works, right? You know that the internet is full of boxes. Boxes like routers, firewalls, gateways, load balancers, all sorts of fun things. Devices that sit between you and that server in the other end that you want to talk to. All those are middle boxes. They all run software, sort of mostly just sending data, you know, one packet from that side away to that side. Just fiddle a little bit with it in between, but it'll help you make the internet better, right? And these boxes, they run software and they know how the network works today. They know how it works today or how it worked yesterday, but they have no idea how it works tomorrow. And they tend to then also see that if it doesn't work like it works today, it's bad and we throw it away. And all these middle boxes, they are upgraded far more slowly than your edge boxes, like your browser at home. It updates every week, right? You run a browser that updated it yesterday or tomorrow or next week. And even in the server side, you actually upgrade it every now and then. Those boxes in between, not so much. They bought it a few years ago, it still works fine. So, the edges, they update. The middle, they don't. What happens then? Yeah, they're ossificated. So, just to illustrate, that's me and the server I'm communicating with. You know, I go through different boxes over the network, and those are all middle boxes. They are all running old software. They know how the internet worked a while back. So this getting stuck in time, ossification, it makes that we couldn't really do HTTP 2 in clear text because A lot of these boxes, they know that TCP over port 80, that means HTTP 1. So they are helpful and help connections do HTTP 1 better. So if you speak another protocol over that same port, a lot of that breaks because the box is in between. And we can also fix things like we can improve TCP. There was this great effort to introduce the TCP fast open, TFO, a long time ago. Actually, the spec is almost 10 years old by now. But it's basically to improve TCP, send data earlier in the handshake. Great idea. A lot of boxes in between. What happens? Doesn't work, really. Because a lot of these boxes, they see these new bits coming. New bit, bad, didn't exist before. Throw it away. So in the end, the TCP fast open turned out to be a fairly slow open in most, well, not in most cases, but in enough number of cases that it turned out that no browser and no sort of big operating system are using TFO today because of that. And that sort of goes on. The same pattern is followed everywhere. We only see TCP and UDP over the internet today because we can't really introduce new protocols because all these boxes, they only know about TCP and UDP. Your NAT and router at home, it only knows TCP and UDP. Try another protocol, doesn't really work, it'll throw it away. We introduced a new compression algorithm for the HTTP. Awesome, Brotley, much better than the previous gzip. Doesn't really work in clear text because, yeah, there are boxes in there. They know what HTTP compression is. So if you show HTTP compression, they will ruin it for you because they know it's gzip only. So, yeah, the paradigm goes on and on and on. That is ossification. Sort of, we did it once. It's really hard to change because a lot of boxes out there, they know how to do it. Unless we encrypt it, right? Hide it from the boxes. Just a random byte stream. They don't know what it is. We can send it through if they don't know it. So that is what we do. So we introduce something so that we can innovate here in spite of all this ossification. Fun. Introducing QUIC. So QUIC is then a new transport protocol to handle this problem, fix or work around all those fun boxes on the internet that are sort of trying to prevent us from doing things. This is based on, again, on some fun experiments done by Google. Google did basically the same approach when they worked on Speedy back in the days that later turned out to become HTTP2. An experiment by Google gone to IETF and turned out to be a standard protocol. In this case, it's another experiment by Google. They introduced it a long time ago and tried it out. They have a fairly well-known, well-used client, and they have fairly well-used server-side services. So an excellent position to run some experiments on all of us who are using their clients and services. So yeah, sort of, they tried it out and it proved to work. You can actually introduce a new transport protocol, send stuff over the internet in a new way, and it works, and it's actually fixed a lot of things. So they thought it was a great idea. Let's do this. Let's make a standard out of this. Let's take this to the IETF and document how it works, and we'll ship it to the world, and everyone can deploy this and run it in their own systems. So the IETF created a working group and basically said, good idea, but we can't really do the way you did it because it's too icky. We can't really squish all the layers together and just, send everything like that. We need to make it into a transport protocol with an application protocol on top of it. So while Google made everything just one squishy thing that sent HTTP2 frames of UDP magically that ended up in the other end, IETF said that, sure, we can do this as a protocol, as a standard, but we need to do it the proper way. We make a transport protocol and we make an application protocol on top of that. That application protocol, that should be HTTP to start with, but the transport protocol, that's just a TCP-like thing. And we document them, and we make them as two layers, which then was completely different from what Google actually did. So they're both called QUIC still. So that's the Google QUIC and that's the IETF QUIC. They're completely different, but they're both QUIC. So just for your information. Hopefully, one of those will be forgotten over the years and one will remain, but no, yeah, that's not the situation right now. So with this, we can fix this TCP header line blocking. You know, we had one connection. If we lost one packet, all the streams over that connection would be waiting for that single packet that was lost. We can fix this if we just make a new protocol. We can also improve those. We don't need those three-way handshakes for TCP and TLS handshakes on top of that. A lot of handshakes to just get up to a new connection. We can fix that maybe. And maybe we can fix that TFO thing I said that we couldn't do. We can actually do that in a new protocol if we do it right from the beginning. And so on. And if we encrypt everything, and even more than before, more than TCP, hide even more things from all those boxes in between, maybe we can actually keep improving this protocol in the future. Maybe. So, we can't introduce a new protocol, I just said before, and then I said we introduce a new protocol. Yeah? We build it on top of UDP. UDP exists, it's there, we build a protocol on top of it. We keep TCP and UDP, they are the only ones, right? So we build everything on top of that. And we basically just treat UDP as the new IP. It's there, we can just send data over it. And we build everything on top of that, like a new layer, a new sort of TCP-like thing on top of UDP. With built-in TLS. So, let me emphasize, on top of UDP doesn't mean that it actually is UDP, because UDP, you know, you just send a lot of stuff, you don't know if it arrives there, it can actually end up in the other order, there's no flow control, you don't really know. You send a lot of data, it might arrive there or not. With QUIC, you just use the UDP delivery mechanism, but you implement a new stack on top of that. You make sure that you're retransmitting things, you add connections, resends, flow control, congestion control, and all of that. And then when you're at it, when you make a new transport protocol, when you sort of implement TLS from the beginning, start over, what do you fix when you implement TLS from the beginning? Oh, sorry, TCP from the beginning, TCP plus TLS. Sure, you make sure that you provide streams from the beginning, because you can put that then into the transport protocol. Instead of, in the HTTP2 days, we added streams into HTTP2, but now we can put it already in the transport protocol. You'll soon realize why that makes a difference. But sure, so we add in streams in the transport protocol. All those streams, they are independent in this case. We fixed the TCP header line blocking problem, because so if you lose one of these little packets this time, when we did it with TCP, we lost a packet, all streams had to wait, because that's how TCP works. But in this case, we designed a new protocol that if we lose a packet, only those streams that are actually in that packet have to wait. All the other streams can actually continue, because the protocol is made to be able to lose individual packets, and the other streams can continue. Suddenly we fixed the TCP head of line problem, and we can actually get much better throughput or behavior in a packet loss situation. They're independent. They are in order, but independent, which basically means that if you're, in the future, when you do HTTP3 server, they can send an image in one order, like image A first, image B afterwards, and they can end up in the client side in the other order, because they're independent. Fun. So basically it means that in the TCP case, you have this chain thing. There are individual links. If you lose one of these, if you lose the red one, the green stream can't continue, right? Because they're connected. You have to wait for the red one to come back before both of them can continue. But in the QUIC case, they're more independent. You can lose a yellow one, and the blue one can continue. The yellow one has to wait, but until that packet is retransmitted. But they're independent, so the streams go on. So, and this is a transport protocol and with an application protocol on top of it. So in theory, then we can add other protocols on top of the transport protocol, other than HTTP, even though the working group right now is only saying we're only focusing on HTTP right now. So there is actually no other protocol right now, but the idea is to, in the future, make other application protocols on top of that. DNS was mentioned early on. There are discussions about others, WebRTC, blah, we can just think of whatever, actually. So then, HTTP3 is the HTTP done over this new transport protocol? Because HTTP2 was made over TCP, HTTP3 is done over QUIC, because you can't really make HTTP2 over QUIC anymore, because QUIC is a different protocol, different transport protocol with different characteristics. But it's still the same HTTP. That's the client, that's the server. We still do the request, you know, method and verbs and headers and the body, and we do the response the same way. We get a response code and everything. We get headers back, we get a body back. The same way we've always done it. We know this. HTTP has been like this since HTTP 1 at least, 1996. The headers, the verbs, they're going to remain. If you're only looking at that part of the protocol, that's the same thing. So HTTP 1 introduced, it did everything in ASCII over TCP. HTTP 2 did binary with multiplexed over TCP. And in HTTP 3, we do the same thing again. We just squish it around a little bit, and we do it in binary, but over multiplexed QUIC this time. Yeah, what does it matter, right? So HTTP 2 is, so rather HTTP 3. What does HTTP 3 do then that HTTP 2 didn't? Not a lot different actually. I mean, apart from replacing everything underneath, it's basically the same thing. So this is how an HTTP 2 stack looks like. You know, TCP on top of IP. On the internet we always have TLS there because it doesn't work in the cleared really, and we do HTTP 2 over that, plain and simple. In the HTTP 3 case, then we do IP, and we put this UDP layer in between that. We just have that because we need UDP. So we add QUIC on top of that with TLS embedded because we do encryption always and everything, and it's TLS 1.3. And we put HTTP 3 on top of that. Fun, a lot of new stuff. So looking at then feature-wise, how does HTTP 3 compare to HTTP 2? They're very similar. Basically, they differ in that while the streams are independent in HTTP 3, there's no clear text version of HTTP 3 because you can't do clear text quick. And there are sort of subtle differences. There's a different header compression and things like that. There's a different early data, and there's a much faster handshake with HTTP 3, but all that thanks to QUIC. From the higher level, HTTP-wise, they're very similar. HTTP 3 is going to be faster in some regards. I'll get back to some of it, because we do much faster handshakes. QUIC offers 0 RTT handshakes if you already communicated with the server before, so you can basically set up a connection and go really, really fast with 0 RTTs, which is a lot fewer RTTs than you do with HTTP 2 and TLS. And it actually has then, presumably, early data that works, so it fixes the TFO problems from the TCP TLS cases, and you can actually send more data even earlier in the handshake. So the idea being that a browser or an HTTP client can get data out to the server much faster than before. The independent streams, of course, then also make that in a packet loss situation, in a bad network situation, the streams that are not affected by the lost packages, they can still go on, so it makes it much better in a packet loss situation. This is still early days, so I wish I had good numbers to show you, but I don't. So this is the theory. Hopefully it'll hold in the real world as well. Google did some numbers and experiments early on how it works for them with their version of QUIC, and it proved to make a small, you gained time in a lot of different situations and in a lot of different aspects like that, but I've chosen not to show you that because Google QUIC, as I mentioned, Google QUIC is not IETF QUIC. So I'm sure that there will be numbers, and there will be a lot of discussions about if the numbers are actually good enough for you to use this tomorrow or not. Because I'll show you some reasons why you won't also. So, but let's just go back then and said HTTP, HTTPS done over TCP, right? Through the years, since the late 80s. And we use HTTPS URL since we agreed that we're going to use HTTPS everywhere anyway, so we're talking about HTTPS : / and we use them everywhere. We can't just change them. There's not going to be an HTTP3 or HTTP3S : / That's not going to happen. There's still HTTPS : / So how are the clients going to switch to HTTP3 in this case? Because HTTP3 is over UDP, right? QUIC UDP. So, yeah. Then we introduced a while ago, actually, so this isn't actually a new thing for HTTP3, it's actually already there, but there's this thing called alt service, or alt SVC : header in HTTP. It was made for in association with HTTP2. But it basically says, like that pointing finger, by the way, I also run something over there, and that's me too, and I might run another protocol on another port somewhere over there. So it can actually say, hey, my HTTP3 server is over there, so if you can speak HTTP3, talk to me there, which of course can be the same server. So the idea being then that the client connects to the server, gets to know about it using HTTP3 somewhere, and connects to HTTP3 either in the background or the next connection attempt. Easy peasy, maybe. It doesn't really work that good, so that's sort of, yeah, if everything works fine, that's fine. So it turns out that if you run this on the internet, there's somewhere around 3 to 7% of all QUIC connections that don't work because of UDP. So you don't, a lot of companies, organizations, networks, they just block UDP because who would use UDP over the network? Well, you use it for DNS results or for NTP or something, but before this point in time, you didn't really use it for high-speed internet browsing, right? So either the organizations block it completely just to avoid DDoS attacks and something, or they rate limit it. So if you happen to use UDP, it turns out to be really, really slow. So it's really complicated now because as a client, you now need to have a fallback, because you know that a lot of your connections will fail, so you always have to have another option in sort of up your sleeve. What happens when the QUIC connection fails? You need to have a fallback. So it's going to be a lot of that, complications. When do you fall back? And you know, when you connect to your HTTP3 server at home and you just put your laptop down and you bring it to work and you're opening it again, will the HTTP3 connection work when you open your laptop? Maybe, maybe not. So the clients are now going to have to raise the new one with the old one. Complicated. And then it turns out that when you implement this in the server side, QUIC is really, really CPU intensive. We're talking 2 to 3 times the CPU to manage the same bandwidth. That's a lot of CPU. So again, going back to then, what gain are you getting out of this? Maybe you don't gain that much. Maybe a few % faster connections for a few of your users isn't worth 2 or 3 times the CPU. Maybe. And this, of course, why is it that CPU intensive? Because of it's not hardware offloaded properly. It uses new ways of doing TLS. I'll just mention another thing about that soon. So it's early days. It'll be better, but now it's really a CPU hog. And it also is because, ironically enough, UDP is really slow in Linux. So we've been tweaking and optimizing TCP for decades, so we know how to do TCP, and we've used it for our servers, and it's really, really streamlined. We haven't done so much with UDP. So now it turns out UDP isn't that good in Linux. It's getting there. People are putting attention on this, so it'll improve over time, surely. But now it's a difficult situation. And there's a funny TLS layer in QUIC. Instead of doing TLS messages, TLS frames, like you did with TCP, you have to do TLS messages with none of the open sort of TLS library support. So you have to get new APIs or new libraries and everything, so it'll be huge obstacles. All QUIC stacks are user-land, which means that all of them are implemented, and different applications are then going to link with different QUIC libraries, and we're going to see different behaviors, and there's no standard QUIC API, so you kind of get married to one of those APIs when you pick it for your application, and it's going to be difficult when, And there are, of course, a lack of tools. Wireshark is on the ball, so they're providing a good tool, but we're lacking there. This is meant to ship in July this year. I'm sure that won't happen, but it still says so in the charter for the IETF. I think the hope is within this year. We'll see. So there are a lot of implementations, a lot of focus, a lot of big brands. They're putting in a lot of manpower into this. They all write their own implementations. Most of them have their own TLS implementations too, because of that API thing. So they have to. Okay, and no browser is supporting this yet. I know that both Safari and Chrome are saying that they have their own development versions in-house. There's this race. I'm trying to push them all to see which one will win, which will have the first public version of HTTP3. And none of the big servers have HTTP3 support in any public version yet, and curl doesn't either. So, not really there. So then, that is what it is, and it's coming. But I think, based on all these obstacles, HTTP3 will take time. It won't be a hit the first day, and it'll certainly grow slower than HTTP2 did, and HTTP2 didn't really take off immediately either. But because of these challenges, the TLS things, and a lot of obstacles, the CPU performance, a lot of things to work on. So I'm pretty sure that a large percentage of users will just sit back and say, HTTP2 is good for us for now. We'll just wait it out and see what happens here. But the QUIC is here for the long term. I think QUIC is often then referred to the new thing to work with in a post-TCP world, thinking this might be the protocol that actually replaces TCP long term. So maybe we shouldn't really care about what happens the next 2-3 years. Maybe we're talking about the next 20 years. Maybe this will be the foundation for what we're building in the future and a more long-term aspect. And of course, even when QUIC and HTTP3 ships, QUIC version 1 ships and HTTP3, there are a lot of things that people have sort of postponed from the QUIC v1. They want to work on this multipath and forward error correction and unreliable streams and of course many more application protocols. Why stop with HTTP? I mentioned a few others. So there are more protocols that people want to do over QUIC going further. So as soon as QUIC v1 is shipped, maybe not in July, maybe in Christmas, but it doesn't matter. As soon as that happens, a lot of people are going to jump on to make QUIC v2, and there's going to be a lot of efforts on doing more application protocols. So that's what I wanted to wrap up with. HTTP3 is coming. I don't know when, but soon. Thank you.
Thanks. Thanks, Daniel, so much for this great insight in those protocols and technologies working the back from our perspective. Yeah, it's really, I didn't understand anything. Maybe you understood a little bit more, yeah? So
I think one did over there.
Oh, cool. That's the guy, yeah. Thank you very much. Und jetzt gehe ich wieder aufs Deutsche über. Wie gesagt, wenn ihr wollt, nochmal da drüben gibt es nochmal Ballroom. Es gibt noch ein bisschen Freibier, nochmal die Gelegenheit, ein bisschen miteinander zu reden, sich auszutauschen. Einige Speaker werden noch da sein. Schönen Abend wünsche ich euch und bis morgen.
Constrained by processes that were made for a different era, were made for a different world, a world of certainty.
Be comfortable with the fact that you don't know, that you, I mean, no one's going to know everything, and if this is still something that's scary or something that's new, that's okay, and that's normal.
So a mechanic can look at the car and analyse what's wrong with the car. You can look at your code and go, I'm expecting this outcome, and so I can close that gap.